In the earlier lecture, we saw how to convert a partial differential equation into a finite difference equation. And we took many different partial differential equations, and using the different schemes, using different finite difference schemes, we converted the partial differential equation into a finite difference equation, and we followed a certain scheme which is we discussed the FTCS, that is forward in time and backward in space. Centered in space. So forward or backward in time, it depends upon what you are going to do, whether you are going to look for the evolution or the history. So that depends upon whether you forward or backward in time. But commonly we write it as a FTCS, where it is a forward in time and centered in space. So that is the typical that is one guideline by which you have to convert the partial differential equation into a finite difference equation. Fine. So, and in this lecture, we will see, after constructing the finite difference equation, how we are going to seek a solution to that equation. So, we will particularly consider two types of problems, as we discussed numerically. When you are looking for a numerical solution of a partial differential equation, what matters is whether the problem is a boundary value problem or initial value problem. Okay, and in the first we will see how to solve a boundary value problem numerically, or whatever, computationally, whatever we can say. So that we are going to see to the first, and after discussing about how the solution of the boundary value problem, then we will go into the initial value problem. If you remember, in the boundary value problem, what we said is a partial differential equation insert in the variable u, which is a function of x and y. What we do is we provide the value of u in a closed boundary. Along the boundary, the value of u is known, and what we want to know is the value of the function u of x in the interior of the interior of this region. So this is what we are trying to solve in a boundary value problem. Okay, and we also took a simple example of a boundary value problem. Let us try to maintain the same problem. It is simple, and we'll try to see how we are going to solve that boundary value problem by using this finite difference method. That's what we discussed earlier. So first, let us take the boundary value problem as the Poisson's equation, that is del square u by del x square plus del square u by del y square equal to rho of x comma y. So this is the boundary value problem which we want to solve, and what we do is the u is provided, the u of x comma y is given over the closed surface C, which is given here. So when you give that, you want to find out how we are going to solve this equation. So the first step is convert this equation into a finite difference equation. So we can see both x and y are space, so we have to use the center difference scheme. Anyway, it is a second derivative, we have to use only center difference we can use. So when the first and foremost thing is to discretize the variable u in terms of x and y. Okay, the first step is to discretize our variable u, that is u of x comma y. We are going to write it as u of I comma j, and let I corresponds to I will goes from 0, 1, 2, 3 up to say some n, and this corresponds to variable x, and j goes from 0, 1, 2, 3 up to m, and this corresponds to variable y. Well, fine. So, and to make our we will use some simplistic boundary conditions, where the boundary conditions are constants. What I am saying is, say me at certain y, this is the provided with this bold dot dashed line. So let us consider this is to be the boundary condition. This is a closed surface, and we want to seek the solution of u of I in the interior of this region. So we are going to divide x into equally spaced grids, and that I denote it as a y I, and x is after dividing x into equally spaced grids, and we are going to divide y also into evenly spaced grids, and that we define by j here. And what we are doing is, for the interval width, we are choosing it as to be h for x and k for y. So this is how we have discretized the function u of x y, and we try to find the value of u x y at the grid points. As I said, we can't when you're going numerically, we are not going to ask anywhere else in between, only at the grid points you will try to find the solution of it. So in the boundary value problem, we are going to arrive, given these boundary conditions, what will be the value of the function at those grid points. We will arrive it in a one shot. We will see as we go along, we'll see what do we mean by it. First we will convert this partial differential equation into a finite difference equation. So we can see this is a partial derivative, this derivative is on x and y which has space, so we have to use the center difference. Otherwise also it is a second derivative, so we can only use a center difference. So when you use a center difference scheme, depending upon the way how we discretized our u and u will be, so this will be u of so this will be his second derivative is on x, so this is going to be I plus 1 j minus 2 times u of ij plus u of I minus 1 j divided by the interval width for the case of hx is h, so this is going to become h square, and that plus, and then we are going the second derivative in y, and y will be the corresponding index for the variable y is j, so this is going to be u of j plus 1 I minus 2 times u of j I plus u of j minus 1 I divided by k square, where k is the interval width for the y what you have written here. Fine, and this should be equal to, the right hand side is a continuous function rho which can be x and y. Of course we have to discretize this also, because we know the values of x and y only at the grid points, so we don't have anything in between, so this also is going to become rho of ij. So this is how we have, this is the finite difference equation for the partial differential equation what we have considered here, that is a Poisson's equation. So we can do a bit of jugglery rearranging this equation. What we can write, so if I introduce a term alpha equal to h square by k square, then we can rewrite this equation as u of I plus 1 j plus u of I minus 1 j plus alpha times u of I j plus 1 plus alpha times u of I j minus 1 minus 2 times 1 plus alpha times u of ij will be equal to h square rho of ij. This is nothing but we just what we have done is we have divided by multiplied by h square all over, so this becomes h square by k square, which are writing it as alpha, and I combine this u of ij both the cases together. That's how I got this equation. So this is the equation. So let me call this one as 1. So, and this is the equation we have to solve. So by rearranging. Now if you carefully see here, what we have is, this is the u, this is basically the two indices u of ij, where your I goes from 0 to n and j goes from 0 to m. We can do a jugglery. Instead of having this equation in two indices, we can convert this equation into a single indices. Means, for example, I can write u of ij, say something like equivalent to u of l. So how am I going to do is, instead of two indices, what I'm going to do, I will do this 0, 1, 2, 3, 4, 5, 6, 7 up to m, and when I come here, I'm going to write this as m plus 1, m plus 2, m plus 3, m plus 4, m plus 5, go on like this. I will go up to 2m, then 2m plus 1, 2m plus 2. I can keep counting. In that way, I can convert these two indices ij into a single index, which we call it as a UL. The way how am I going to the conversion of two indices into a single index, I'm sure we have shown it here, where this is 0, 1, 2, 3 up to, okay, remember this will have total m plus 1 terms because 0 to m. So this, I'm starting from 0, this will be m plus 1, m plus 2, m plus 3, m plus 4, and go on, and the final term will be 2m plus 1, and then this is going to be 2m plus 2, 2m plus 3, 2m plus 4 to 3m plus 2, because it starts from 0. This is the way we go on, and this is the way, by counting like this, we can convert the two indices, the variable u in two indices, into a single index L. So the way, how do we, so what is the algorithm which basically converts these two indices into a single index L? So we have two indices I and j into single index L will be, it is simple, you can check it out. L will be equal to I into m plus 1 plus j. So you can see here, when I equal to 0, for example, when I equal to 0, so j goes from, if you remember j goes from 0 term, so I equal to 0 corresponds to this column 0 to m. When I equal to 1, so this is going to become m plus 1, so m plus 1, and j goes from 0 to m, so this is going to correspond to this equation. This will correspond to this column, and for I equal to 2, we can keep checking that. So this is how. So this is the equation which converts our u in the function u, which is in two indices, into a single index cell. So now, so therefore, after representing, introducing L, so what we will have is u of ij will become u of L. So now, when you have u of ij is equal to u of L, so what is going to happen for u of I plus 1j? So this will be what? This will be equal to, so when in this case you are replacing I with I plus 1 and j with j only, so this is going to give us, so L will be equal to, this is I, we have replaced is, or let me call, I won't call it as a L, so let me call this as some, say something like, or L star. L star will be I, we replaced as I plus 1, so this is going to become I plus 1 into m plus 1 plus j. So this will become I into m plus 1 plus j plus m plus 1, or this is nothing but our L equal to I m plus 1 plus j, this is L, so this whole term is going to become L, so this is going to be L plus m plus 1. Therefore u of I plus 1 j is going to become u of L plus m plus 1. So similarly, next term we have a I minus 1 and j, so this is going to be u of I minus 1 times j will become, when you put that in that case, or let me call it as a L star, that will be I minus 1 times m plus 1 plus j, so this you can clearly find it out. So this will be L minus m plus 1, or what we can call it as L minus m minus 1. So this is going to be u of L minus m minus 1. Cool. And then we have the other terms will be u of ij plus 1. Yeah. So what this going to become is u of ij minus 1. So all we can see, this will be just a j minus 1. So this whole term is going to become L. So this is going to be u of L minus 1, and similarly u of where we have j plus 1 is also there in this state. So u of I into j plus 1 will become u of L plus 1. Therefore this equations, so this equation, this finite difference equation what we constructed, that will become, where will I write it? Fine, so let me make a copy of it. So oops. So this equation is going to become, so what we have done is, so we will transform this equation is equal to, it is u of I of j plus 1, that is going to be u of L plus m plus 1. So this will be u of L plus m plus 1 plus u of L minus m minus 1 plus alpha times j plus 1 is nothing but u of L plus 1 and plus alpha times u of L minus 1 minus 2 times 1 plus alpha, of course u of ij, that's what we wrote it as u of L, that will be u of L and h square. And remember this one again, this will be rho of ij, rho of ij is nothing but rho of L. So by this equation, so this is an interesting equation. So what we have done is, so we have converted the index, the variable with two indices into a single index. Okay, so what's the advantage of it? We will see it very soon, and this is how gives us a chance of trying to seek the solution all in a one shot rather than in an initial value problem, which we will discuss later. Okay, so now this is an interesting equation. So this equation, let me write this one as 2. Why this is interesting is, this equation is valid at all the interior points only. This equation is not valid at the boundaries. Why it is not valid at the boundaries? We will see it soon. Okay, so let us take for example, let us consider, okay, why it is not valid at the boundary. We will take up certain examples of these indices, and we will see how this is going to how this equation will look like in this grid plot. Okay, before we see how this equation is going to connect those grid points, let us see, because of this converting from the two indices into a single index, how this boundary conditions is going to change. If you remember, initially our boundary conditions were we didn't mention about the boundary conditions, though we wrote it. The boundary conditions here are for I equal to 0. If you see earlier what was the boundary conditions we had, so we had the boundary conditions as for I equal to 0, j goes from 0, 1, 2 up to m, and I equal to say something like n. So j goes from 0, 1, 2, 3 up to m. And then another thing is, this is the boundary condition for j equal to 0. I goes from 0, 1, 2, 3 up to n, and j equal to m, and I goes from 0, 1, 2, 3 up to n. So where I have those corresponding u of I, j, they were the boundary conditions. So this is what the boundary conditions we have mentioned here. Now after converting the double index S2 of ij into a single index, which we did just now, that is this one, after converting this, how these boundary conditions are going to change, let us have a look at it. So if you see here now after this conversion, so first one is simple. So when the first condition, I can say this is a one boundary condition. So that is simple, that the boundary condition your L will be equal to 0 to m. So there is 0, 1, 2, 3 up to m. This is the one boundary condition. So and then we have to write down the next boundary condition. That will be, say for example, let us call from here. This how do we, if you try to see from the pattern what you are getting, 0, m plus 1, 2m plus 2, 3m plus 3. So and this next one will be 4m plus 4, 5m plus 5. So if we keep on doing that, what you are going to get after the nth point, it will be n into m plus 1 or n into m plus n, or you can write nm plus n of m plus 1. So then this boundary condition is going to be L will be equal to n of n of m plus 1 comma n of m plus 1 plus 1 n of m plus 1 plus 2. You go on up to the final term will be n of m plus 1 plus m, because there are total n terms. So this is going to be n of m plus 1 plus m. So this is the two boundary conditions we wrote. Now let us try to write down this boundary conditions. Of course 0 we have taken already here, so let us write from here. So then this L will going to be m plus 1, correct, this will be m plus 1, that is this one, and this is 2 times m plus 1, 2 times m plus 1, and this is 3 times m plus 1, 3 times m plus 1, and then 4 times m plus 1, keep on going, and the final term will be n times m plus 1. Well, but we shouldn't take this point, we should take one point before and where I write it out. So what will be the previous point will be n minus 1 m plus 1, because n times m plus 1 is already taken here. So this point is always will become double count. So this is how the third boundary condition. Finally we have to go for the fourth boundary condition, that is this. So we can see this is 2m plus 1, 3m plus 2, 4m plus 3. We can see the pattern very nicely. So this is going to become L equal to 2m plus 1, 3m plus 2, 4m plus 3. So it go on. If you see, the wordlet term will be n plus n minus 1. That's what it will become. So because there are total n terms, so it will become nm plus n minus 1. That's how we got this number. So these are the boundary conditions. So this is how the boundary conditions get modified after you converting from the double index to a single index. So, and this is we have to remember. And now as I come, let us what I was earlier telling. So let us see that more closely. That is this equation. So after converting your double index to a single index, this is how the finite difference equation get modified. And I said this finite difference equation is valid only at the interior points, only at the interior points and not at the boundary. Means for these regions, for at these boundaries, this equation is not valid for these points. How we are going to how to understand that? Let us take order for certain cases of L. Okay, and when you consider certain cases of L, we can see how this equation connects the neighboring grid points, and this will give us an idea why this equation is not valid at the boundaries. Let us consider the case for L equal to m plus 3. So when we convert, when we replace in the place of L, we write this L as m plus 3. That's m plus 3 is some point. When L is m plus 3 means this is what I am going to write this point. So u of ij, what we have now, it's a u of L, that is going to be the u of L, m plus 3. So if you write down this equation for m plus 3, what this equation is going to become will be, this is going to will get modified as u of L equal to m plus 3. So this is going to become 2m plus 4 plus, and when you put back this m plus 3 here, what we are going to get is u of 2, because this is m plus 3, so minus 1 become 2, plus alpha times L plus 1, that is m plus 3 plus 1, that is going to u of m plus 4, u of m plus 4 plus alpha times u of L minus 1. L minus 1 means m plus 2. So m plus 2 minus 2 times 1 plus alpha times u of L will be equal to h square into rho of L. Well, so let us now carefully see that. So u of L, so L equal to m plus 3, so this is the point, we are writing it as L. So this connects, what are the other grid points? So 2m plus 4, 2m plus 4 is here, and 2 is here. Let me use a different color, that makes it clear. So 2m plus 4 is here, and 2 is here, and the m plus 4 is here, and m plus 2 is here, and this is our u of L. So what we saw is, this equation basically connects the 4 nearest neighbors. So this is how this equation is represented here. How this equation connects for each different values of L, this is how this equation is connected. So now let us go for another condition. So we said that this is valid at the interior point. Of course, we choose L equal to m plus 3, that's the interior point. So therefore it is valid very nicely. So let us take the point in the boundary. Okay, for example, let us consider the point L equal to this boundary. Suppose let's take this point. So that is 2m plus 2. So when L becomes 2m plus 2, this equation is going to become u of, this is going to be 3m plus 3, and then 2m plus 2, when I put it here, what we are going to get is u of m plus 1, correct? Yes, m plus 1, and then when I put this one here, what we are going to get is alpha times u of 2m plus 3 plus alpha times u of 2m plus 1 minus 2 times 1 plus alpha u of L equal to h square, h square into rho of L. Okay, so this is the equation we get when we connect this point, when the L equal to 10 plus 2. Let us try to see how these points are being connected. If you see it carefully, 3m plus 3, that is 3m plus 3, that is a point here, fine, and then m plus 1, that's a point here, and then it's a 2m plus 3, that's a point here, and next if you see the point, this is 2m plus 1, 2m plus 1, the point lies here. So, and then, so now if you see, instead of taking a point here, so since we used by converting the index into 1, it wrongly took the point to be this. So that means it had considered this point as the nearest neighbor, which is actually not. So therefore this equation, this is not there, so this equation is not going to be valid at these regions. And similarly you can find out for all these boundary points, this equation will not be valid. Therefore this equation is going to be valid only at the interior points. Okay, so the first step is all the ULs, we have to remove all the ULs corresponding to the boundary, remove those equations. So we will, remaining equations only we can be solved. So for example, you can see this is m plus 1 and n plus 1. So if I remove all this point, the equations corresponding where UL falls on the boundary, we have to remove all those equations. That means there will be two equations. So you will, if you actually see for m plus 1 and n plus 1, this equation can actually provide us m plus 1 into n plus 1 equations. But as we said, this is not completely correct because we have to remove all ULs which fall on the boundaries. Therefore, finally, how many equations you will get is, so for example, this is one boundary, this is one boundary, so what will be left over will be, as you said, m plus 1. Now you minus this one and this one, what is going to become m minus 1 here, and then similarly here is going to be n minus 1. So we are not going to get this equation. So this, what we'll get to the number of equation will be m minus 1 into n minus 1 equations. So finally what we end up is m minus 1 into n minus 1 equations given in the form which is given here. So that is u of L plus m plus 1 plus u of L minus m minus 1 plus alpha times u of L plus 1 plus alpha times u of L minus 1 minus 2 times 1 plus alpha times u 1 plus alpha u of L. This is equal to height square rho L. So this is the m plus 1 into n plus 1 equations which we have to solve. This is the m plus 1 equation we have to solve, and you can see, so basically what happened, we have to write down this equation for all L's falling into intermediate regions, in the interior regions. That's actually, in fact, that's what you have to find out. We have to find out the solution of these regions. So eventually we are going to get a system of equations. The number of system of equations is going to be m minus 1 into L minus 1 equations. So eventually then this is again what we end up is. What we end up is finally the whole problem of solving the finite difference, because once if you solve all these interior points for all this u of 3m plus 4, 3m plus 5, all the interior points, that's what we want. That's what the solution we required from this partial differential equation. So, and that's what here. So ultimately the whole finite after converting the partial differential equation into a finite differential equation and doing all this jugglery, what we end up is finally we have to solve this system of m minus 1 n minus 1 system of linear equations. So this will come down to be a matrix form. Let us write as A dot u will be equal to, say, some what you call, put it as a B. So this is a, so now if you see, so this is a m minus 1 n minus equation. So the dimension of this matrix A, when you write it as in a matrix form, the dimension of this matrix A is going to be m minus 1 n minus 1 cross or by m minus 1 n minus 1. So, and this is a challenge, how we are going to handle this matrix. Before we go into how we are going to handle this matrix, let us see, for example, if you carefully look at this equation. So that's what, if you remember this equation, so what we have is this equation will be something, okay, one thing I forgot to tell you. So these equations will have all these equations whenever, right, if you remember when I wrote this equation here, this when L equal to m plus 3, that's here. So when L equal to m plus 3, one point will be the boundary point, which is not an unknown, which is a known quantity. So in this case, that is u of 2. So this is a known quantity. We have to take this one in the other side. So this is going to become code like minus u of 2. So then what we write is, we in the left hand side we write all the unknowns, in the right hand side we keep the known quantities. So that's why you have to roll off all the boundary points. When you are writing the program, you have to construct or roll all these boundary values to the right hand side and make a matrix equation of this form. And that's how you will get a matrix equation of m minus 1 into n minus 1, m minus 1 n minus 1 into m minus 1 n minus 1 matrix equation. Now if you see, suppose you are solving this problem for a different boundary condition. So what if you see this whole Poisson's equation problem what you are solving, if you want to solve this Poisson's equation for a different boundary condition, if you carefully look, the only quantity which is going to change is B. The matrix A will not change at all, because only the boundary conditions go on row of here or for a different row of L. Even if you have a different row, functional form of row, all which is going to change is the only B, and the matrix A will remain intact. So the better method to solve this matrix problem is the LU decomposition. So what we do is we compose this matrix A into L dot U and keep it ready, and then for a different B values we keep solving this one. And this is very important here, because I will come in a short while. This matrix A will be this A is going to become a huge matrix. We will see that, a huge matrix, because you can see from the number of bits. So, and this is going to computationally very intensive. So we can't afford for doing every B. We can't afford to solve this matrix equation A by Gauss elimination or Gauss Jordan, those methods. So LU decomposition is the most preferable method to solve these types of problems. Now coming back to the matrix M. Matrix A. So what we have done is, so we basically so this is basically m cross n and m minus 1 n minus 1 m minus 1 n 1 cross matrix. So now let us try to see how much elements this matrix is going to have. For instance, for any nominal calculation, if you consider m equal to 100 and n equal to 100, which is actually not at all unacceptable, because when you try to solve a partial differential equations, you see n equal to 100 and m equal to 100 are not a good choice. You have to at least make it 200, 300, 500, or sometimes even thousands you have to do it out. So let us take a very reasonable grid points of m equal to 100 and n equal to 100. So okay, so m minus 1 equal 99, so we can approximate it as 100. Is not going to really change. So m minus 1 into n minus 1 is typically going to be 10 to the power of 4. So therefore the dimension of this matrix A will be 10 to the power of 4 into 10 to the power of 4, and that is going to be equal to 10 to the power of 8. So what you are going to have, so this matrix A is going to have 10 to the power of 8 elements. And if you remember in the initial class, when we are dealing the matrix problems, one of the biggest problem when we face when we solve the matrix is when the two equations become very closely represent a linear combination. In that case, you will end up a singular matrix, and the one way to avoid is to use a double precision, because if you don't use single precision, matrix problem usually fails. So it's always better to have a double precision. So then for 10 to the power of 8, and typically for a double precision, it will occupy typically say 8 bytes for. So if it takes 8 bytes of memory, then for 10 to the power of 8, so I can call typically it is 10 bytes approximately. So to save this 10 to the power of 8 matrix element, what we have is, well, and the memory equation, the memory requirement will be 10 to the power of 8 into the value of byte, that's typically 10 bytes. So this is going to be 10 to the power of 9 bytes, or it's typically 1 gigabyte. So, and this is alarming. So just to save this matrix A, it appears you need 1 gigabyte of memory to store this matrix. And this is not the case, though it appears to be alarming. But the people were using to solve these Poisson's equations with at those periods when the computer hard disk was 640 or say 600 or 700 MB. So the people were somehow handling this matrix and all. So And there comes an important part. If you were to see the matrix, there comes something what we discussed earlier. Of course, we didn't go into detail of it. That's something what we saw is a sparse matrix. If you carefully see this matrix equation, it is not all the 10 to the power of 8 elements or all m minus 1, n minus 1 into n minus 1, all these elements are non-zero. Only very few elements are non-zero. Okay, to see it, so let us consider the case of let's consider a simple case of n equal to say 5 and m equal to 4. In that case, what happens? So then this equation is going to become 5 minus 1 into 4 minus 1 cross 5 minus 1, 4 minus 1, and that is going to be 4 into 3. Okay, this is 12 cross 12 matrices. This is the matrix A will be. The matrix A will be like this, and this sign will be like this. If you carefully look, okay, I have to bring down that equation so that you can see it here. Yeah, okay, fine. So if you see that this equation is actually, earlier also we say it takes only 4 terms. U of L corresponds to one will join with 4 other neighboring terms. Other terms it won't connect at all. So this will eventually reduce this matrix into a kind of a sparse matrix. I'm sorry, I shouldn't write here x and y. I just use x and y to make it simpler. But what I mean is x is nothing but minus 2 times 1 plus alpha, and y I am right. Y I mean is y equal to alpha. In fact, all this y should be alpha. I don't know why I wrote it like y. This all should be alpha. Okay, so you can assume it. So x is going to be minus 2 into 1 plus alpha. So this is how. So if you try to construct the matrix form, this equation into a matrix form for the case of n equal to 5 and m equal to 4, what you will see is this is how the matrix equation will look like. And here I forgot to roll down the boundary conditions. Of course, when you are doing it, you have to do it carefully. So the boundary conditions come out, or you can take, okay, yeah, I have written as B. So the B involves all these row h square row of ij as well, row of L as well as the boundary condition. So this is how we write out. So now if you see, most of the elements are 0 here. So what we have, 3 diagonal elements are non-zero, and the next of diagonal element is 0, and the next diagonal element is 1. The same thing below also. So this type of matrix is basically what happened. We have a tridiagonal matrix with one of diagonal matrix to be non-zero. This type of matrices is generally called as tridiagonal matrix with fringes. So this is the type of matrix you will get. So if you actually see, solving this all PDE eventually will end up in these types of sparse matrix, which has a very definite pattern. Something for here we saw for a Poisson's equation. When you write a matrix Poisson's equation, what you're going to end up is a tridiagonal matrix with fringes. For some other equations, you will end up a different type of matrices. And solving this matrix is going to give us this different all the u terms, which is I have already taken care of the boundary here. So that's why this is there. Removing the boundary return all these u values. If you try to make the grid point corresponding to n equal to 5 and m equal to 4, you will see these are all the grid points we have to actually identify. So by solving the matrix for different b, we can get down to u, and that's how a boundary value problem is being solved computationally. So ultimately it ends up you have to solve this matrix. So the boundary value problem eventually boils down to a matrix problem, and solving this matrix of huge order. Here I took n equal to 5, m equal to 4. This is won't really happen in if this was not allowed in the array case, it will be typically n equal to 500, m equal to 500, then it's going to be a huge matrix, we have to solve it. So the partial differential boundary value problem eventually boils down to solving a partial differential, solving a matrix equation, and in the solution of the matrix equation lies our the answer to the problem. Well, this is how a boundary value problem is being solved in solved numerically. And in the next lecture, it will be a very short lecture, so we will see how we solve an initial value problem using this finite difference methods. Thank you.